Hey friends. So, yeah, usually we do neural nets in low dimensions, but we wanted to canonicalize Boolean functions because there's sort of the at least intuition that, like, because neural nets are composing hyperplanes that, like if you rotate, like if you have two functions and you can rotate them into each other, then kind of from the perspective of a neural net, they're kind of like the same function. Because you can rotate the hyperplane in the same way that you can rotate the hypercube. So, we'd kind of like the idea of like for the 65,536 four-dimensional Boolean functions, we'd like to reduce the and then just study representative examples from each a conjugacy class, maybe? Yeah, I don't know enough group theory to... or they could be orbits. It's like one of those. Like, for example, the function that is constantly false. Under any rotation, it'll be the same function. So, like, it is in its own, I think, equivalency class is probably the term. And then also, like, functions that accept a single input. Those are all in the same equivalency class because you can rotate one input into any other input. So, like, a counterexample is like in two dimensions, you could, like the functions that accept two inputs, there's two equivalency classes because one class is the two inputs are direct neighbors, and then the other equivalency class is the two inputs are, two apart, like they're on the diagonal. So those would be different classes because you cannot, like in particular, you cannot change pairwise distance. You can't change distances under rotations of a hypercube. So, so we're trying to develop like a script where you have like three-dimensional functions and four-dimensional functions, and we just like you take a function and then you go through all rotations, and then like that's an equivalency class, and then you go to the next function, and you check and see if it already exists in one of the equivalency classes. So anyways, it's that particular process of starting with a function table and, like applying all rotations to it, that we're like trying to actually cache out into like actual code, because but an even more prefiguratory problem is just how do you actually generate all of the elements of the all rotations of the hypercube, aka the automorphism group, I think they're the same concept. Yeah, we are a little conjectural on, like, because we're just trying to capture the idea that, like, you can rotate hyperplanes. So therefore, rotations of the hypercube we want to get rid of. We want to mod them out. Yeah, but, like, it's not clear if that is equivalent to, like, all automorphisms. But anyway, we're just going to work with automorphisms because I looked it up once, and I kind of know how to generate them. And yeah, we're gonna try to see if we can go from this one piece of information. So, like, I know that the number of automorphisms, which, by the way, like, these are just permutations, or the number of elements of the, is, for the n cube is 2 power n factorial. And that's, like, the argument is because you pick the origin, and then you can, like, pick any, like, under rotation, like, if you imagine 3D intuition, or even 2D intuition, you can pick any point to be at the origin, so that's 2 power n choices. And then you have to assign the neighbors, like the Hamming distance 1 neighbors of the point that you pick to be at the origin. You have to assign the neighbors to the axes. And then apparently, in a way that I cannot really necessarily see, that determines, like, every other assignment of so like, we're gonna play around with that. I mean, it kind of, that totally makes sense in 2 dimensions. So maybe there's like a recursive, maybe there's like a recursion. Actually, yeah, I think there is a recursion. So yeah. Okay, well, let me, like, I'm gonna draw something, though, okay? I'm gonna draw a 2 cube. Just to, yeah, I'm gonna draw some 2 cubes. If this works, cause, yeah, okay, so, right, so, yeah, we have, like, right, so we have, like, the 2 cube, and, like, the standard, like, I guess that's the identity element or something. So what we're saying is like, you can pick any one of these points to be at the origin, like, and also, like, we're just arbitrarily specifying the bottom left as the origin. I'm gonna delete these real fast just because it's unrelated. And right, so anyway, like, like, we can pick, say, like, this guy to be at the origin. So we do him at the origin, and his 2 neighbors are 1, 1 and dash dash. So you can put dash dash there and 1, 1 there, or you can, do the other way, 1, 1 dash dash. And then, of course, there's only one other element in either case, so that solves that problem. But also, yeah, let me write the count, because that kind of yeah, so like the number of elements we're saying is, yeah, like 2 power n factorial, right? And this is like, this corresponds to origin or igen, and then this corresponds to like axis assignment. Yeah. Right. So I might have just proved this to myself. I'll look at it in 3 dimensions. Actually, or like we should just skip immediately to 4 dimensions. Nah. Also, this is also an assignment. Yes. Yeah, so I mean, like when you go to 3 dimensions, yeah, I mean, it's the same thing, because it's like you can just consider like a 2-dimensional face. Yeah, because like everything's independent. Okay, well let me I'll draw it out anyway. Cause yeah, I'll draw it out anyway. So although like it's highly annoying to draw a 3 cube. We'll do it. Yeah, like, jeez. Like, so, right. So we're saying like this is that axis, I guess. No, I think you just, like, you want to do that. And then this one. And then that, so that's like the front face. You know, and then you just like copy. Except you flip this bit. We're flipping that bit. Yeah. It is beautiful. I mean, it's not really. It kind of looks like garbage, but that's fine. So, yeah. Okay, this is, yeah, we're doing really well. We're doing really good. Yeah. Congrats. Thank you. Okay, so, that's like a 3 cube. And, right. So, if we pick an arbitrary, like, you know, again, this, you know, like this is the origin, just by convention, doesn't matter. W log, as they say. That's kind of weird. You have like log and then W log. Has anybody ever thought of that? Okay, so we're gonna do the thing where you just you pick an arbitrary, you know, we're gonna pick this guy to be the origin, right? So we're gonna draw him there. Now this guy has 3 neighbors. You know, this one, that one, and that one. And we have to assign. I mean, this much is clear. The thing that's less clear is that determines everything else. Although I think there is a pretty easy, like, recursion happening, but, I guess I could see if I could develop the recursion, but anyway, so, like, that would prove this. Which is kind of conjectural, but but then like once we've proved that, then we still have to like cash it out in terms of like flipping bits and whatnot. Okay, so anyway, we're assigning neighbors of this guy, 1 dash, and you know, he has this as a neighbor. I'll just highlight the neighbors just to be that's a neighbor, that's a neighbor, that's a neighbor. I guess kind of a interesting observation immediately is that like you could fix this neighbor if you so desired, but I do not desire. So I'm just gonna put like him over here, and then put the 1 here. Oh no, then it fixed that guy. Oh, I didn't want to fix anything. That's fine. That's fine. Alright, so... Oh no, yeah, but I should write that actually. So that guy gets fixed. And, yeah, so like we now have... you know, this, you know, like we have this bottom corner assigned. And then, yeah, I mean, everything else you can see is determined. Although I don't know if this generalizes. But I mean, like, you know, you have an unknown point here, and you're like, one of its neighbors is all ones. One of its neighbors is -1 dash. Actually, is that determined? I don't even know if that's actually determined. Because that might not be determined actually, because you're saying like what is a point, you know, that is one away from both of these points, because these points are 2 away from each other, as you would expect. So I mean, like 1 dash would be 1, but that's already assigned. Can you flip that bit? Right, no, it has to be closer to both, so you can only flip the bits where they are similar. So then you have -1 and so 1 dash is already assigned, so therefore this has to be -1, and yeah, so that's going to be like a similar logic for this one. And yeah. See, I don't know if I can generalize that. Because like if you're in dimensions, I mean like if you're in like I mean, okay, there is a recursive argument, I think, because I mean, yeah, there is a recursive argument, which is that you just pick, like, you know, because we have it proven for the two-dimensional case. Like, we just assume it's proven for the two-dimensional case. So yeah, you just focus on the two-dimensional case. You're like, all right, I'm going to pick, you know, any point here, and then I'm going to select 2 points for this face. These have to be neighbors. And then that fixes this guy. And then that fixes this opposing face, 3-dimensional cube, and those would all be fixed. Okay, but yeah, but that implies that you're just selecting two neighbors and then everything is fixed, and that's not even what the argument is. So, well, yeah, I think it's like, oh yeah, I think there's a degree of freedom in that, you know, like you're you're selecting which, so when we selected the two-dimensional guys, I mean, yeah, like we're assigning like dimensions. So yeah, so I mean we selected this guy, right? And then we're saying like this neighbor is different on this dimension. And then we're saying like this neighbor over here, I think yeah, like that would be the next one we assign. We're saying he's different on this, that dimension, the last dimension. Yeah, so therefore, yeah, so that's basically all you're picking. You're just picking, you know, when I go in a particular direction, what does that correspond to in the, yeah, that vaguely makes sense, kind of. Let's do a four-dimensional. Oh shoot! I don't think I want to do four. Nah, it's fine because we're just gonna copy this, and it'll be very cool. I just have to delete all this stuff. That one, that one, that one. These guys. That one, that one. This one, that one, that one. Yeah, good job. Thanks. Okay, so like we're going to 4 dimensions. This has never been done before. Oh, I think I wrecked my computer. Like, oh wait, did it work? Cause like I copy paste. Oh, haha. It was messing with me. Yeah. How should we? I don't know. I guess you just like put. Oh, that didn't do what I thought it did. Okay, I need to paste what I copied, right? There we go. All right. So, right. Yeah, but like then we have to draw all of the new edges. Yeah, that's gonna be a lot of edges, actually. That's fine. I'll just draw them all. That's fine. Everything's cool. So that guy goes here. This guy goes there. And then like, you know, that, oh dang, that went off the screen. That one, this one, and the last one. That one didn't go well. You kind of want them to not overlap. Alright. Okay, this is like a 4-dimensional hypercube. And everybody's impressed. Everybody's like, holy sh... Guys, you can't use profanity. Or maybe you can, I don't know. Like, I don't know. Okay, then we're just gonna go ahead and put in that... yeah, this is going really well. It's also very cool to me that this thickness is different from the old thickness on the marker. Okay, alright, so we have 4-dimensional hypercubes, and we're just gonna, I guess we're just gonna redo that assignment thing. So like, yeah, we're just gonna pick, again, this is the origin. This is always the origin, right? It's like blue origin. You know? And, and, yeah, I forgot what I was talking about. Okay, so, okay, listen, we're gonna pick this guy. This guy? Guys, I use guy in a gender-neutral fashion. I'm just FYI. So, no, I'm not sure that'll be good, actually. Like, cause he's only... How is he only one away? Oh, no, no, okay. That's fine. Yeah, alright, we're gonna pick that guy. Alright, so we have 1-1-1. This is our new assignment. This corresponds to the 2 power n part. And then, you know, and so like his, his neighbors are like that guy, and that guy over there, and this guy, and now he has a 4th dimensional neighbor, right? It's like space-time. Oh, that's really weird, actually, that it flattened out. I wasn't expecting that. That's cool. That's very cool. Okay, and right. So anyway, this guy, like, his neighbors are fixed, right? Like, they're determined by the definition of the 4 cube. Also, string theory. No, it doesn't involve string theory, but... Or does it? Like, I don't... So, okay, that's a neighbor. This is a neighbor. And then... That's a neighbor. And then that's a neighbor, right? So all we have to do, the claim is all you have to do is assign these 4 guys to these things, and then everything else is determined. And I think that makes sense, right? I mean, like, because like we're doing like a little recursion argument, and because I mean, like this, these neighbors, right? Like this one just, this one differs on that dimension, 2nd dimension, 3rd dimension, 4th dimension, right? And then, but that has to be true for every other thing in the cube. Like, whenever you go in that dimension, it has to be the same index bit that's changing. So, yeah. Right? Yeah. Yeah, man. So if you... Right, okay. So, like, if you do the 2-dimensional assign, it's like, we're just gonna pick, like, this guy and this guy, and we're gonna put this guy over here, 1 dash, 1 dash, and then we're gonna put the other one up here, 1, 1, 1, 1. Right, and, we're saying, like, this guy differs on that dimension, and the other guy differed on the last dimension. And then, right, so there's still one more choice, though. Because when you go from here to here, you can still, you can differ on this dimension, or you can differ on this dimension. And, I think that makes sense. But the question then is, how do you, like, cash that out in terms of bit flips? And I'm kind of feeling like the answer is you just permute ooh, yeah. I think, yeah. Like, you would like, so if you had all, that must be you just have, right, so like you just represent all the points, the 2 power n points as like a matrix, and then you like, right, and then this assignment part is just a permutation of the columns, and then the 2 power n part is you're selecting columns to bit flip the entire column. Yeah. And then to go back to canonicity, canonicalism. Is that right though? I mean, is that good? I really feel that that's good because I mean, like, you know, okay, so just you know, like if we just pick this one, no, we already did that. Right, okay, so if we pick this one for here, --1 right, that means we're saying, right, that means, right, so everything else is determined, like, yeah, like everything else is determined because, okay, which one's, we assigned that one, what was the other one? Okay, that one. Okay, so, alright, so this one becomes 1-1, and that is differing on the 3rd bit. So that means, everything else is determined because, yeah, let's just go through and fill it out. So, when you cross in this direction, you're flipping the last bit. So that means, like, this one is --1 --1 and this one is like 1 and like right, and then you can argue, like, when you're going up, you're flipping this middle bit. So that means we have --111 here. And yeah, we also have, again, we're flipping that one, so it's like --11 and yeah, right, and then you just copy over this entire thing and you flip the corresponding bit. So like in particular, all of these should magically have the same bit on that one, and they all have 1. Yeah, okay, that's cool. Okay, I think we understand that. Yeah, so that was fairly productive, I guess. Thanks for watching.